Okay, so now let's actually connect our parallel resistors up to a voltage source in parallel and see what happens there. So we're going to connect our voltage source in parallel with the resistors so that the positive terminal is connected to each of the resistors, as is the negative terminal, or the ground terminal, if you want to call it that. Okay, so the positive terminal is directly connected to the top of each resistor, and the negative is connected to the bottom. All right, so that means that the voltage is going to be the same across parallel elements. So what we're saying is that if we have 0 volts here, because that's our ground node, then we've got 0 volts here and 0 volts here, because nothing happened to change that all the way through. And if here we have 12 volts, we're going to see 12 volts here and 12 volts here. So for a parallel circuit, we don't have the same current through each of our resistors. We have the same voltage across parallel resistors. So the voltage stays the same across the parallel elements. Okay, so if two elements are in parallel, the voltage across them must be the same. Okay. However, if the voltage across two elements is the same, that doesn't necessarily mean that they're in parallel, right? They have to have 2 points in common for that to happen. We're talking about voltage is the same if they're connected on the top and in the bottom. Okay, so for a single source parallel network, the source current is always the sum of the individual branch currents. So the current coming from our source is going to divide across each of those resistors. So some of the current will go through one resistor, some of the current will go through the other resistor. Remember, in series, what we found was the opposite. We had the voltage dividing across the series resistors, whereas in parallel, we're going to see the current divide there, and we're going to have a current divider rule to look at with that. All right, so let's actually work through our parallel circuit here and see how this works. Okay, so I've got a 27 volt source in parallel with my 9 and my 18. So how do we determine what current we're pulling from our source? Really, very similarly to what we did for our series circuits, we're going to do the same for our parallel circuits. We're going to first find our total resistance. Okay, so we've got a 9 ohm resistor and an 18 ohm resistor in parallel. So I'm going to calculate 1 over 9 plus 1 over 18, and then I'm going to invert that at the end. You could also do product over the sums here. This is, we just have 2 resistors in parallel, so you could do product over the sums. And that gives us 6 ohms of total resistance. Okay, so what that means is looking from the source is going to see 6 ohms of total resistance there. Okay, and that's going to help us determine what our source current is. So we have E over RT. This is not any different from our series circuit. Remember, Ohm's law applies the same way no matter what circuit it is. The source current is always going to be the total voltage you apply divided by the total resistance of the circuit. So we've got 27 volts there divided by 6 ohms. So that gives us about 4.5 amperes of current there. Okay, so if I draw that in, that means that we're supplying 4.5 amps of current to the circuit. Now, what else do we need to know? We need to know V1 and V2. So in this case, remember, our R1 and R2 are connected to the positive terminal of our voltage source, and they're also connected to the negative terminal of the voltage source. So V1 and V2 are exactly the source voltage in this case, which is 27 volts. And that's really the important thing to remember about your parallel circuit there, is that the voltage stays the same across parallel elements, right? There's nothing between the 27 volt and the 9 ohm resistor to change that voltage, so it's going to see the same voltage there. So if we want to find I1, that's going to be V1 over R1. And remember, V1 we just found was 27 volts because it's in parallel with the source, divided by that 9 ohms of resistance, means that we have 3 amps of current here. And our I2 is going to be V2 over R2, where again we have 27 volts, but this time divided by 18 ohms. So that's going to be about 1.5 amps of current there, going this way. So if you notice, we have 4.5 amps coming into this junction right here, where we have some of our current will go this way and some of our current will go this way to the right. So if we have 3 amps going this way and 1.5 amps going this way, that makes sense, right? You've got 4.5 amps coming into a node, 3 amps leaves through the 9 ohm resistor, and 1.5 through the 18 ohm resistor. Also think about Ohm's law here. Does it make sense that we have more current through the 9 ohm resistor than we do for the 18, given that they have the same voltage drop across them? It does, right? The more resistance we have, the more it limits that current. So the 18 ohm resistor is going to limit the current more than the 9 ohm resistor. Notice too, the 9 ohm resistor is about half the value of the 18 ohm resistor, right? And yet we see twice the current through R1 that we do through R2. That's going to be a really important thing to think about as well as we go through the rest of this chapter. So let's look at another example here, very similar to what we just did. So I'm just going to work through it the same way. What is our R2, our RT, I'm sorry, total resistance? We've got an 8 ohm and a 24 ohm resistor. So when we calculate our total resistance, we get 6 ohms. And make sure you're practicing this with me with your calculator. If you have any questions on this at all, if you're not getting the 6 ohms out of your calculator that I'm getting, make sure you reach out to me for help, because this is probably a very simple thing that we can work on together, and you don't want to be stuck on this, okay? So that will give us a way to find our source current. What current's required by the source depends on the resistance of our circuit. So if we have E over RT, which we do, we've got 36 volts and 6 ohms of resistance, meaning we'd have 6 amps of current required by the source. All right, so how do we find I1 and I2? Well, I1 is going to be V1 over R1. I2 is going to be V2 over R2. But remember, V1 equals V2 in this case, which equals our source voltage of 36 volts. So we just plug that 36 volts in here into our Ohm's law equation here. 36 divided by 8 means we have 4.5 amps there. And 36 volts divided by 24 means that we have 1.5 amps here. So let me draw that in. So here we've got 4.5 amps and 1.5 amps. Again, that 6 amps is coming in right here. 4.5 leave that way. That leaves 1.5 to go toward the R2. And that actually makes sense, right? Okay, so for our next circuit here, I'm going to just kind of show you the calculations. Now we've got 3 different resistors in parallel, the 10K, the 1.2K, and the 6.8K. So when we find our RT, notice that it's 925 almost 926 ohms. And that makes sense. It's going to be lower than our smallest resistor, which is just 1200 ohms. So that makes sense. When we plug that into Ohm's law and divide 24 by that RT, we see that we have almost 26 milliamps of current that we're supplying to these three branches. And then with I1, that would be V1 over 10K, I2 would be V2 over 1.2K, and V3 is I3 is V3 over the 6.8K. V1, V2, and V3 are all equal to our voltage source because they're in parallel with the voltage source. And we see the same voltage throughout the parallel branches there. So 24 divided by each of those resistors tells me I've got 2.4 milliamps here, 20 milliamps here. That's a significant portion of our source current, and 3.5 milliamps here. When we add all of those currents together, those branch currents, we call those branch currents, when we add those together here, we get 25.93, which was our source current. Okay, so branch currents there. All right, let's work a slightly different problem this time. So here we're given, let's see, RT, we're given I1, we know R1, and we know R2. What we don't have would be E, our source current, R3, and I2. So let's talk about how to find all of these. Okay, so again, this is very similar to some problems we worked with series circuits, and what you want to do is find a place where you can apply your Ohm's law, which is a place where you have two of voltage, current, and resistance. If you have any two, you can find the third using Ohm's law. So look at R1 right here. With R1, we know the resistance and we know the current. So what does that mean we can find? We can find the voltage there. So V1 is I1 times R1, and we know we've got 4 amps there times 10 ohms of resistance. So we must have 40 volts there. Now, how does that help us? Well, notice all of these resistors are in parallel. And down here, you see they're all connected. They all show this ground connection right here. Well, that means that they're actually connected, okay, to each other as well. So anytime you see multiple ground connections in the circuit, think they're all connected to each other at that point, okay, because ground is one point in your circuit. Okay, so they're connected in parallel on the other end as well. So that means the same 40 volts that I have here is actually my source voltage, as well as the voltage drop across R2, as well as the voltage drop across R3, because they're all in parallel with each other. All right, so what can I find next? Well, now if you look at R2, we know V2 and we know R2. So with our 40 volts there that we just found and our 20 ohms there, we must have 2 amps of current going through the 20 ohm resistor. And now what do we want to find? Oh, we can find I sub S, because I sub S is E over RT. We now know E is 40 volts and RT is 4 ohms. So we must be supplying 10 amps to our circuit. Now the only thing left is to find R3 out here. R3. And what do we need to know to find R3 using Ohm's law? Well, that would be V3 over I3. We know that V3 is 40 volts. We just need I3, right? Which would be right here. Now, how we could find that is basically looking at the current coming in, we've got 10 amps of current coming in from the source, and we see that we've got 4 amps leaving here and 2 amps leaving here. So if we want, we could say 10 amps minus 4 minus 2 amps would have to equal I3, right? Whatever's left has to be I3. Well, 10 minus 4 is 6, minus 2 is 4. So if I3 is 4 and V3 is 40, oh, I'm sorry, that's amperes, not ohms. So that would mean that R3 would be 10 ohms. Now, is there a way to check this? Absolutely there is. Okay, remember RT should be 1 over R1 plus 1 over R2 plus 1 over R3. So if you plug in your the 2 known resistors and then our third resistor that we just found, you should get 4 ohms that we have here for RT. Okay, and we do. That actually does work out. All right, so before we move on to our next section, I want to talk about measuring voltage and current in a parallel circuit. So here, this would be our voltage source or a voltage supply. You're probably used to batteries. Well, in the lab, we actually have a voltage supply we can connect up to the circuit, where our positive terminal would be connected here to one end of each resistor. Our negative would be connected to the other end of each resistor, and that then connects these 2 resistors together in parallel. To measure voltage, remember, we do not disturb the circuit. We connect our voltmeter in parallel with that resistor to measure the voltage across the resistor. So when you were connecting your voltmeter in your last lab and you were measuring around that resistor, you're actually putting that meter in parallel with the resistor. We just didn't necessarily know that that was called parallel. So you're leaving your circuit intact and you're just measuring across. So notice across R1 we have a measurement of 12 volts, which is the voltage we're applying to the circuit. And across R2 we're measuring 12 volts, which again is the voltage we're applying to the circuit. Each of those resistors is in parallel with the source, so you should see 12 volts across each. Now to measure the current, remember what we have to do is we have to make the meter a part of the circuit. So we wire the meter in series with whatever component we're measuring the current through. So if we want the source current, we need to put it in series with the source, meaning we take the red lead from the source, connect it to the red lead of our ammeter, and then from the black lead we actually go to the circuit. So the current has to go through the meter before it gets to the circuit in order for us to measure our source current. And you see that we're measuring 16 milliamps there. Now if we want to measure the current through a branch of the circuit, just through one of the resistors, we would have the circuit set up just like we did in that first circuit right here, except then what we're going to do is take away one end of our resistor and insert the meter right at that point, okay, at one point. So instead of going straight into the resistor, we're going to go into the meter and then to the resistor. But notice I did not disturb the connection here from R2 to the source. And that's very important. You don't want to take away a connection elsewhere in the circuit to measure the current here. Okay, so you'll be practicing this as we build our circuits in Multisim, and hopefully someday you'll be able to do this in the lab as well. Okay. Okay, so in the next video we'll talk about power distribution in our parallel circuit.